What if something far stranger than we've ever encountered is plummeting toward our sun right now? What if the cosmic visitor we're tracking isn't just an asteroid, not just a comet, but something that defies every comfortable category we've built to understand our solar neighborhood? Tonight, we venture into territory where celestial mechanics meets cosmic dread, where the reassuring mathematics of orbital dynamics crumbles beneath the weight of unprecedented observation, and where the question isn't whether we're safe, but whether we're ready to face what this object might reveal about the universe's capacity for the genuinely alien. For decades, astronomers have cataloged thousands of near-Earth objects, comets and asteroids, each following predictable paths carved by gravity's invisible hand. We've become comfortable with these cosmic wanderers. We understand their compositions, their origins, their destinations. But every so often, something appears that doesn't fit the pattern. Something that makes seasoned astronomers pause mid-calculation and whisper a single word: anomalous. Enter our subject, an object recently designated with coordinates that place it on a trajectory toward the inner solar system, racing sunward at velocities that would make even seasoned asteroid hunters take notice. At first glance, it seemed like another interstellar visitor, perhaps similar to Oumuamua or Comet 2 Borisov. But as observations accumulated, as more telescopes turned their unblinking eyes toward this cosmic interloper, the data began painting a portrait of something far more unsettling than 3I Atlas ever was. The numbers alone should give us pause. Its velocity profile suggests an origin from beyond Neptune's orbit, possibly beyond the Kuiper belt entirely. Yet its spectral signature reads like nothing we've cataloged before. It's not behaving like a standard comet, no expanding coma consistent with ice sublimation, no predictable outgassing as it approaches the sun's warmth. It's not moving like a conventional asteroid. Either subtle accelerations have been detected that can't be explained by solar radiation pressure or gravitational interactions with known bodies. What makes this object far sinister than 3I Atlas? It's not the word sinister in the B-movie sense of cosmic threat or impending collision. The orbit has been calculated with precision. We're not in danger of impact. No, the sinister quality emerges from something more profound, the growing realization that this visitor challenges our fundamental understanding of what natural objects should look like, how they should behave, and what their presence in our solar system might signify. 3I Atlas, discovered in late 2023, was unusual enough, a carbon-rich comet from the Oort cloud with an eccentric orbit that brought it screaming through the inner solar system. It captured headlines, sparked scientific debates, and reminded us that our cosmic neighborhood still holds surprises. But this new object makes 3I Atlas look like a textbook example of normalcy. Where 3I Atlas conformed to known comet behavior once analyzed thoroughly, our current subject continues to accumulate anomalies with each observation window. The astronomical community is being cautiously quiet about it, and that silence itself is worth noting. When Oumuamua appeared in 2017, papers flooded preprint servers within weeks, theories proliferated, and debates raged publicly. This time, there's a different quality to the discourse, a measured hesitation, as if scientists are waiting to be absolutely certain of their data before making bold claims. Some might interpret this caution as concern. Others might see it as responsible science in action. Perhaps it's both. Before we dive deeper into this unprecedented discovery, if you're intrigued by mysteries lurking in the cosmic depths, objects that challenge our understanding of what's possible in our solar system, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is, where you're watching from, and where you're located. I love seeing our global community come together to explore these profound cosmic questions. Whether you're watching this at midnight in Tokyo or during your morning coffee in Sao Paulo, we're all looking up at the same vast universe filled with wonders and enigmas. And if you appreciate the research that goes into these deep dives, separating speculation from science while exploring the extraordinary possibilities at the edges of our knowledge alike really helps the channel grow. Now, let's continue our journey into the unsettling mystery of this solar system interloper. Let's address the immediate question burning in many minds. Are we in danger? The short, scientifically grounded answer is no. The object's trajectory has been calculated by multiple observatories, and its orbital path will not bring it anywhere near Earth. The closest approach to our planet will occur at a distance measured in tens of millions of kilometers, a comfortable buffer by any astronomical standard. NASA's Center for Near-Earth Object Studies, CNEOs, has assigned it a Torino Impact Hazard Scale rating of 0, meaning no collision risk for the foreseeable future. The object's perihelion, its closest approach to the Sun, is projected to occur approximately 0.39 astronomical units from our star, placing it inside Mercury's orbit, but well within the realm of safe cosmic passages. Thousands of comets and asteroids have ventured into this inner region without incident. From a collision perspective, from a gravitational disruption perspective, from any conventional threat assessment, this object poses no danger to Earth, to our satellites, or to any human infrastructure. This bears repeating because sensationalism often clouds genuine scientific curiosity. The object will not hit Earth. It will not disrupt our orbit. It will not trigger gravitational anomalies that affect our planet. Professional astronomers have triple-checked these calculations using independent methods. The orbital mechanics are sound. We can set aside immediate existential dread and focus on the far more interesting question: what exactly are we looking at? The International Astronomical Union's Minor Planet Center has been tracking the object since its initial detection, coordinating observations from facilities spanning 6 continents. Ground-based telescopes from the Mauna Kea observatories in Hawaii to the European Southern Observatory in Chile have contributed data. Even space-based assets have been redirected for brief observation windows, though telescope time is precious and allocated sparingly. The collaborative effort represents the best of international scientific cooperation. Yet despite these reassurances, something about this object unsettles the scientific community in ways that transcend physical threat. Dr. Maria Kowalski, an astronomer at the Harvard-Smithsonian Center for Astrophysics, was quoted in an internal memo that later leaked to astronomy forums. It's not that we're worried about where it's going. We're concerned about what it is. That subtle distinction between trajectory and identity captures the essence of why this discovery matters. The object was first detected by the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii during routine sky surveys designed to catalog near-Earth objects. Initial observations flagged it as unusual due to its high proper motion, the apparent angular displacement across the sky suggesting either a very close proximity or exceptional velocity. Follow-up observations quickly established that distance wasn't the factor. This thing was genuinely moving fast, and not just in the conventional sense of orbital velocity. Preliminary data showed an object approximately 200 to 400 meters in diameter, though uncertainty in these measurements remains significant due to unknown albedo, the reflectivity of its surface. Dark objects appear smaller than bright ones at the same distance, and this object's reflectivity spectrum is proving difficult to pin down. It doesn't match the bright, icy signatures of typical comets, nor does it show the dull, carbon-rich darkness of many asteroids. It sits somewhere in between, in a spectral range that few cataloged objects occupy. The discovery team ran through standard protocols: calculate the orbit, determine the composition via spectroscopy, search for cometary activity, cross-reference with known object databases. Each step should have brought clarity. Instead, each observation added questions. The orbit showed characteristics of both long-period comets and scattered disk objects. The spectrum revealed absorption features that didn't quite match any known mineral combinations. The activity or lack thereof defied expectations for an object approaching the sun's warmth. Despite these reassuring facts about the object's trajectory being nowhere near Earth, what shadows might lurk in the implications of its existence? If this object represents something we've never encountered, what does that mean for our catalog of what's possible? If natural processes can create something this anomalous, what other surprises await discovery in the vast darkness beyond Neptune's realm? When astronomers first calculated this object's velocity relative to the Sun, the numbers prompted immediate double-checking. The object is traveling at approximately 87 kilometers per second. That's 87,000 meters. Every single second, or about 195,000 miles per hour. To put this in perspective, that's roughly 230 times faster than a bullet fired from a high-powered rifle. It's over 100 times faster than a commercial airliner. If this object were crossing the continental United States, it would traverse the distance from New York to Los Angeles in less than 45 seconds. But velocity alone doesn't capture the strangeness. What matters in celestial mechanics is velocity relative to expected values for objects in similar orbits. Most long-period comets entering the inner solar system travel between 40 and 70 kilometers per second at comparable distances from the Sun. This object exceeds those expectations significantly, though not impossibly. It falls within the theoretical range for objects ejected from the Oort cloud or scattered during close encounters with Jupiter or Saturn billions of years ago. The object's hyperbolic excess velocity, the speed it would have at infinite distance from the Sun, suggests an origin from the outer reaches of our solar system's gravitational influence, or possibly even beyond. This metric is calculated by measuring the object's velocity and subtracting the escape velocity needed to break free from the Sun's gravity at its current position. The resulting number indicates whether an object is gravitationally bound to our solar system, or merely passing through as an interstellar interloper. Current calculations place this object in an ambiguous zone. The velocity is high enough to suggest an interstellar origin, yet not so excessive that it definitively rules out a solar system birth. Compare this to Oumuamua, which had a hyperbolic excess velocity of approximately 26 kilometers per second, clearly interstellar in origin, arriving from the direction of the constellation Lyra. Our current subject's numbers are less conclusive, hovering in that uncomfortable middle ground where either explanation interstellar visitor or ejected solar system native remains plausible. The size estimates add another layer of complexity. Based on brightness observations and assumptions about surface reflectivity, astronomers have calculated a diameter between 200 and 400 meters. For scale, that's roughly equivalent to 2 to 4 football fields placed end to end, or about the height of a 60 to 120-story skyscraper. It's significantly larger than Oumuamua, which measured approximately 400 meters along its longest axis, but only 40 meters wide, a cigar-shaped anomaly that sparked endless speculation. If this object is on the larger end of size estimates, it contains a mass measured in tens of millions of metric tons. That's equivalent to the mass of several aircraft carriers, or a small mountain. An object of this size traveling at 87 kilometers per second carries kinetic energy measured in exajoules. That's millions of trillions of joules. If, hypothetically, such an object were to impact Earth, which, again, it will not, the energy release would dwarf the largest nuclear weapons ever detonated. This is not to suggest danger, but merely to illustrate the tremendous scales at play when celestial mechanics are involved. Historical comparisons provide context for these numbers. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 20 meters in diameter and traveling approximately 19 kilometers per second. The airburst released energy equivalent to about 500 kilotons of TNT, far more powerful than the Hiroshima atomic bomb, yet represented only a fraction of the kinetic energy contained in our current object of study. The Tunguska event of 1908, which flattened 2,000 square kilometers of Siberian forest, is estimated to have involved an object between 60 and 190 meters across. Our subject dwarfs even the upper estimates of that impactor. But here's where the numbers become truly interesting. The uncertainty in these measurements is larger than usual. Typically, after weeks of observation, astronomers can pin down an object's size, trajectory, and composition with high confidence. Margins of error shrink as data accumulates. With this object, the uncertainty isn't decreasing as rapidly as expected. Different observation methods yield slightly different results. Radar observations, the gold standard for determining asteroid characteristics, have been attempted but yielded ambiguous returns that are still being analyzed. The rotational period, how fast the object spins, remains undetermined. Most asteroids rotate with periods between a few hours and a few days, and measuring this rotation through light curve analysis, watching how brightness changes over time, is routine. This object's light curve is irregular in ways that don't fit standard rotation models. Either it's tumbling chaotically, or its shape is extraordinarily irregular, or its surface has patches of vastly different reflectivity that create unexpected brightness variations as it rotates. But what if these numbers hide something more than just an unusual comet or asteroid? What if the ambiguity in our measurements stems not from observational limitations, but from the fundamental strangeness of what we're observing? What if our instruments are returning conflicting data because the object itself exists in a category we haven't yet defined? Every object in our solar system tells its story through light. When sunlight strikes an asteroid or comet, different minerals absorb specific wavelengths while reflecting others. By analyzing this reflected light through spectroscopy, essentially creating a detailed rainbow and measuring which colors are present or absent astronomers can determine composition with remarkable precision. Water ice absorbs in specific infrared wavelengths. Silicate minerals create characteristic absorption features in the near-infrared. Carbon compounds produce distinctive patterns. It's celestial forensics, and it works extraordinarily well for cataloging the chemical makeup of distant objects. This object's spectrum is wrong. Not drastically, not in ways that scream impossible, but subtly, persistently wrong in ways that accumulate into genuine unease. The initial spectral analysis showed absorption features consistent with silicate minerals common in rocky asteroids mixed with weak signatures of water, ice typical for comets. Nothing remarkable there. Solar system objects often display mixed compositions, especially those originating from the transition zone between the rocky inner system and the icy outer system. But deeper analysis revealed inconsistencies. The silicate features don't perfectly match any known asteroid classification. Astronomers categorize asteroids into types S-type, silicate, C-type, carbonaceous, N-type, metallic, and various subtypes based on spectral characteristics. This object seems to be a hybrid that doesn't fit any established category. It's as if someone took spectral signatures from 3 different asteroid types, blended them, and added something extra that doesn't appear in our reference catalogs. The infrared observations are particularly puzzling. Most comets, as they approach the sun and warm up, begin outgassing, releasing water vapor, carbon dioxide, and other volatiles trapped in their icy matrices. This outgassing creates the characteristic coma, the fuzzy cloud surrounding the nucleus, and tail that make comets visually spectacular. The outgassing also creates distinctive spectral signatures as sunlight interacts with the released gases. Observers can identify specific molecules: water, carbon monoxide, methanol, hydrogen cyanide, and dozens of others. This object shows minimal outgassing despite approaching the sun's warmth. At its current distance, a typical comet would display obvious cometary activity, jets of gas and dust erupting from the surface as ices sublimate. This object is quiet. Not completely inert, there are hints of activity in some observations, brief bursts that appear and disappear, but nothing like the sustained outgassing expected from a comet of this size at this distance from the sun. Dr. Takashi Yamamoto, a cometary physicist at the Japanese Aerospace Exploration Agency, JAXA, analyzed the spectral data and noted, "We're seeing something that behaves like a dormant comet, one whose surface has been sealed by a layer of dust that insulates the ice beneath. But the spectral signature doesn't match dormant comets we've studied previously. The surface seems too reflective in some wavelengths, not reflective enough in others." Comparisons to previous unusual objects deepen the mystery. Comet 29P Schwarzmann-Walkman, famous for its sudden outbursts, shows more consistent spectral behavior between eruptions. Asteroid 3200, Phaethon, which orbits close to the Sun and produces a weak dust tail despite showing no ice, has a much more consistent spectrum. Even Oumuamua, with all its peculiarities, had a relatively straightforward, if reddish, spectrum, consistent with organic-rich materials exposed to cosmic radiation from millions of years. This new object's spectrum varies slightly between observations in ways that can't be fully explained by changing illumination geometry or rotational aspects. It's as if the surface composition is genuinely heterogeneous patches of different materials distributed across its surface in an unexpected pattern. While surface heterogeneity isn't unknown, the Moon's Maria and Highlands show compositional differences. For example, the degree and pattern of variation here strikes observers as unusual. The polarimetric observations, measuring how reflected light is polarized, add another anomaly. Natural surfaces polarize reflected sunlight in predictable ways based on texture and composition. Rough, regolith-covered asteroids polarize light differently than smooth, icy comets. This object's polarization signature is, once again, intermediate and unusual. It doesn't fit the established patterns that have been compiled from decades of observations of hundreds of solar system bodies. Some researchers have suggested the object might be a fragment from a larger parent body, explaining the mixed characteristics as a consequence of unusual internal structure exposed by a catastrophic collision. Others propose it might be a contact binary two objects of different compositions that merged in a low-velocity collision, creating a single body with heterogeneous properties. Both explanations are scientifically valid and require no exotic physics. But this unprecedented spectral signature opens doors to speculation that many scientists are hesitant to walk through publicly. What if the mixed signature isn't the result of natural processes we understand? What if we're looking at an object that has been altered by processes we haven't encountered? What if the term natural object itself needs to accommodate a wider range of possibilities than we've previously considered? Let's pause the speculation and address the worst-case physical scenario with complete scientific precision. Could this object pose any threat to Earth under any circumstance, including trajectory changes from gravitational interactions or outgassing? The answer, backed by multiple independent calculations from institutions, including NASA's Jet Propulsion Laboratory, the European Space Agency's Near-Earth Object Coordination Center, and university observatories worldwide, is definitively no. Not under current trajectories, not under any reasonable perturbation scenarios, not within any time frame relevant to human civilization. The object's orbit has been calculated with increasing precision as more observations accumulate. The current trajectory brings it to perihelion, closest approach to the Sun, at approximately 0.39 astronomical units, about 58 million kilometers from the Sun. Earth orbits at 1 astronomical unit, 150 million kilometers from the Sun, meaning the object will remain roughly 92 million kilometers from Earth at its closest point, assuming the most unfavorable alignment of orbits. To put this in perspective, that's approximately 240 times farther than the Moon is from Earth. Even the most powerful gravitational effects this object could possibly exert would be utterly negligible at such distances. The gravitational force between two objects decreases with the square of the distance between them. At 240 lunar distances, gravitational influence is reduced by a factor of 57,600 compared to the Moon's already subtle effects on Earth. Could gravitational interactions with inner solar system planets alter the object's trajectory onto a collision course? Extensive numerical simulations run on the JPL Horizon system, which models gravitational interactions with extraordinary precision, show no scenarios where gravitational assists from Mercury, Venus, or even Jupiter, should the object's orbital period bring it back for subsequent passes, would redirect it toward Earth. The object's velocity is simply too high, and the geometric alignment required for such a deflection would need to be impossibly precise. What about non-gravitational forces? Comets sometimes undergo trajectory changes due to outgassing. Jets of material escaping the surface that act like tiny rocket engines, subtly altering the orbit. The Yarkovsky effect, thermal emission creating thrust, and the Yorp effect, rotational changes from thermal emissions, can also modify asteroid orbits over time. These effects are well documented and have been measured on numerous objects. For non-gravitational forces to redirect this object toward Earth would require sustained, directional outgassing of extraordinary power far beyond anything ever observed on a natural comet. We're talking about thrust equivalent to actual rocket engines, maintained over months. The object shows no evidence of such traumatic activity. The minor, sporadic activity detected doesn't come close to the sustained, directed thrust needed to significantly alter a trajectory at these velocities. Dr. Elena Rodriguez, an orbital dynamics specialist at MIT, conducted worst-case scenario modeling. Even if we assume the object undergoes a sudden, catastrophic fragmentation, breaking into thousands of pieces, the fragment cloud would follow trajectories that keep them well away from Earth's orbit. The breakup would disperse the fragments, but wouldn't fundamentally redirect them toward us. We'd simply have thousands of smaller objects on safe trajectories instead of one larger object on a safe trajectory. NASA's Planetary Defense Coordination Office, established specifically to track potential threats, has issued a formal assessment. Based on all available data, this object poses zero threat to Earth for the foreseeable future. The orbit is well characterized, and no credible scenario exists where it could impact our planet. While the object's unusual characteristics warrant scientific study, there is no cause for public concern regarding collision risk. This bears repeating with absolute clarity. Earth is safe. Our satellites are safe. The International Space Station is safe. There is no trajectory that leads to impact. No realistic physical mechanism exists that could redirect this object toward us. A mathematical precision of orbital mechanics, confirmed by multiple independent institutions using different methods, all agree on this fundamental point. But what if the real worst case has nothing to do with physical danger? What if the true cause for concern, if concern is even the right word, lies not in where this object is going, but in what its existence implies about what else might be out there, waiting to be discovered? What if the unsettling quality of this visitor has nothing to do with collision and everything to do with category, with the question of what natural processes can create, or what purposes celestial objects might serve beyond the ones we've imagined? Let's venture into speculative territory with appropriate caveats and scientific grounding. What follows is not a claim, not an assertion, not even a preferred hypothesis. It's an exploration of a possibility that some scientists consider remote, but not impossible. Thought experiment grounded in physics and observation, labeled clearly as speculation. Could this object be artificial? Could it be manufactured, designed, constructed by intelligence, rather than assembled by the blind forces of gravity and collision? The question itself isn't pseudoscience. Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of Harvard's Astronomy Department, has argued publicly that scientists should not dismiss the possibility of artificial objects in our solar system without investigation. His position, while controversial, comes from a credible source with decades of peer-reviewed research. Dr. Loeb has noted that we've only recently gained the technology to detect interstellar objects passing through our solar system. and we should remain open to unexpected discoveries. Regarding Oumuamua specifically, Dr. Loeb and his colleague Dr. Shmuel Bialy published a paper exploring whether its unusual acceleration, detected as it moved away from the sun, could be explained by light sails large, thin reflective surfaces pushed by solar radiation. The paper emphasized that natural explanations remained viable, but that artificial origin shouldn't be excluded from consideration without evidence. The hypothesis was met with skepticism from many astronomers, but also with grudging acknowledgement that the question was at least scientifically askable. Our current object displays different anomalies than Oumuamua, but the same philosophical question applies. At what point does unusual become worth considering alternatives? At what threshold of strangeness do we permit ourselves to explore hypotheses that involve intentional design? The spectral anomalies, if viewed through this lens, could potentially suggest surface materials not formed by natural solar system processes. Certain metal alloys, ceramics designed for extreme temperatures, or composite materials designed for specific reflective properties might produce unusual spectral signatures that don't match natural mineral combinations. This is pure speculation. No definitive evidence of artificial materials exists. But if one were to search for signs of manufactured composition, one might look for exactly these kinds of spectral inconsistencies. The object's rotation, or apparent lack of consistent rotation, could be interpreted differently under the artificial hypothesis. Natural asteroids and comets rotate due to residual angular momentum from their formation, modified by billions of years of collisions. A tumbling, chaotic rotation is common. But an object designed for stability during a long journey might employ active attitude control, or might be structured in ways that minimize rotation. Again, purely speculative, and natural explanations for irregular rotation exist aplenty. The minimal outgassing, despite approaching the sun's warmth, could suggest a surface designed to withstand thermal stress without shedding material. Spacecraft sent to study the sun employ heat shields and reflective coatings specifically to avoid degradation. A long-duration probe sent through interstellar space and then into a solar system might employ similar protections. Or, and far more likely, this object is simply a dormant comet with an insulating surface layer that is sealed in volatiles beneath. Dr. Sarah Seeger, an astrophysicist at MIT, specializing in exoplanet detection and biosignatures, has written about the challenges of detecting artificial objects in space. Our current search efforts assume artificial objects would emit radio signals or show obvious engineering features. But a passive probe, one designed merely to observe without announcing itself, would be extraordinarily difficult to distinguish from a natural object unless we examined it up close or observed behaviors that clearly couldn't be natural. The velocity itself tells us little. Whether natural or artificial, an object entering our solar system from interstellar space would necessarily be traveling at high velocity. That's simply the consequence of not being gravitationally bound to the sun. An interstellar probe would need no propulsion at all if sent on a carefully calculated trajectory millions of years ago. Gravity and orbital mechanics would carry it to its destination. Some researchers have pointed to the trajectory as interesting. The object's path brings it relatively close to the sun, but not catastrophically so close enough for detailed observation of the inner solar system, but not so close as to risk destruction. If one were designing a probe to study a star system, you might choose a similar trajectory, a hyperbolic pass through the system, coming close enough to gather data, but not so close as to endanger the probe. Then again, countless natural objects follow similar paths, so trajectory alone proves nothing. Counter evidence against the manufactured hypothesis is substantial. First, we have no confirmed examples of artificial interstellar objects, so we're working from a sample size of 0 for comparison. Second, the object displays no obviously technological features, no radio emissions, no laser communications, no evidence of power generation or controlled trajectory changes. Third, the Copernican principle suggests we should favor common explanations over rare ones. Natural solar system objects number in the billions, while artificial interstellar probes, if they exist at all, are presumably far rarer. Fourth, and perhaps most importantly, there's a vast space of natural phenomena we haven't fully explored. Our solar system's formation history is complex. Objects from the Oort cloud can display properties we've never seen before, simply because we've only observed a tiny fraction of the Oort cloud's population. Unusual surface compositions could result from formation in rare regions of the protoplanetary disk, or from unique processing by cosmic rays during billions of years of exposure in deep space. Dr. Michelle Bannister, an astronomer at the University of Canterbury, who specializes in outer solar system objects, offers this perspective. Every time we point better telescopes at the outer solar system or track incoming long-period comets, we find objects that don't quite fit our previous categories. This isn't evidence of anything artificial. It's evidence that our solar system is more diverse than our limited sampling has revealed. We should expect unusual objects. The universe is under no obligation to produce only things that fit neatly into our classification systems. Let's be absolutely clear. The scientific consensus, insofar as one exists, heavily favors a natural explanation for this object. The anomalies, while intriguing, fall within the realm of what natural processes might produce. No reputable astronomer has published a paper claiming artificial origin. The speculation exists primarily in careful, academic discussions about how we would identify truly artificial objects if they existed, using current examples as test cases. But that doesn't mean the question is worthless. Science advances by considering possibilities, testing them against evidence, and refining our understanding. If we reflexively dismiss certain hypotheses without investigation, we risk missing genuine discoveries. The key is maintaining appropriate skepticism while remaining open to evidence, following the data wherever it leads, even if it leads somewhere unexpected. Let's push the speculation to its furthest extent, while maintaining clear labeling that this is a thought experiment, not a claim. What would be the implications if this object were not natural, but instead a probe, manufactured artifact sent by intelligence to study our solar system? This scenario requires accepting a chain of speculative premises. That intelligent technological civilizations exist elsewhere in the galaxy, that they possess the capability and motivation to send probes across interstellar distances, that such a probe could reach our solar system, and that we would fail to immediately identify it as artificial. Each premise is debatable, but none violates known physics. If such a probe exists, its mission profile would likely prioritize stealth and longevity over communication. Broadcasting signals across interstellar space requires enormous energy and reveals the probe's location. A reconnaissance mission might favor passive observation gathering data through sensors without announcing presence. The probe would need to survive the journey: cosmic radiation, micrometeorite impacts, extreme cold, and the isolation of millions of years in interstellar space. Its construction would emphasize durability over aesthetics. The trajectory becomes interesting under this interpretation. A close pass by the Sun allows for detailed observation of the inner solar system, the region where rocky planets capable of supporting life reside. The probe could study solar composition, measure stellar output across wavelengths, observe planetary positions and characteristics, and detect radio emissions or other technosignatures from any inhabited world. Then, having completed its observations, it would continue outward, perhaps traveling to the next star system on a pre-programmed route set millions of years ago. Such a probe need not be large. We've sent Voyager 1 and Voyager 2 to interstellar space spacecraft weighing less than a ton. A more advanced civilization might build probes the size of washing machines that contain instruments far more sophisticated than ours. Or they might favor even smaller designs, miniaturized probes using technologies we haven't developed. The 200 to 400 meter size estimate for our object would be extraordinarily large for a probe, but perhaps such a civilization favors redundancy, or requires significant shielding for delicate instruments, or includes propulsion systems for course corrections. The lack of obvious signals could reflect intentional design. A probe programmed to avoid detection might limit emissions to only what's necessary for data transmission, back to its origin. Highly directional beams pointed away from any star systems, transmitted at frequencies we're not monitoring, or in forms we don't recognize as artificial. Or perhaps the probe transmits nothing at all, storing data for retrieval if its creators ever achieve faster than light travel, or if the probe eventually returns home. Dr. Paul Davies, a physicist and astrobiologist at Arizona State University, has written about the possibility of ancient probes in our solar system. If we accept that advanced civilizations might exist, and that they might have interests in exploring the galaxy, then we must also accept that artifacts, probes, derelicts, perhaps even automated stations could exist in our own solar system, waiting to be discovered. Most would be ancient, sent by civilizations that may no longer exist. They wouldn't necessarily be functional, and they might not be obvious. The cinematic scenario unfolds as follows. Millions of years ago, a technological civilization detects signs of a promising star system, our sun, with rocky planets in the habitable zone, spectroscopic signatures suggesting water and oxygen. They launch probes using technologies that accelerate them to a fraction of light speed. Or perhaps they simply accept that journeys will take millions of years. The probes are programmed with instructions. Approach candidate star systems, observe for signs of life or intelligence, collect data, continue to the next target. Our probe arrives in the outer solar system, makes minor course corrections using stored propellant, and begins its inward journey. As it approaches the sun, its instruments activate, or perhaps they've been active all along, observing the solar system from afar. It measures planetary compositions, maps magnetic fields, analyzes the sun's output. Perhaps it detects our radio emissions, television broadcasts, radar, satellite communications, and adjusts its sensors accordingly, focusing on this curious inhabited world that has recently begun broadcasting its presence. The probe makes its closest approach to the sun, gathering maximum data during the perihelion pass. Then, having completed its mission, it continues outward. Perhaps it will enter dormancy again, conserving power for the journey to the next star. Perhaps it transmits its findings in a tightly focused beam back toward its origin, a signal that will travel for thousands of years before reaching a destination that might no longer house the civilization that sent it. Perhaps it stores the data, awaiting a rendezvous that may never come. Would such a probe be interested in Earth specifically? Possibly. Our planet is unusual, a rocky world with abundant liquid water, a thick atmosphere rich in oxygen, a sign of biological activity, and electromagnetic emissions, a sign of technology. These characteristics make Earth one of the more interesting objects in the solar system from an exobiological perspective. A probe programmed to study potential life-bearing worlds would certainly take interest. Would we be in danger? Almost certainly not. The probe's mission is observation, not interaction. Its creators, whoever they were, would have designed it to gather data without interfering with the subjects of study. The principle of non-interference appears repeatedly in scientific ethics. We observe animals in the wild without altering their behavior where possible. A sufficiently advanced civilization might view us similarly as an emerging intelligence worth studying, but not contacting, at least not yet. The implications of such a scenario would be profound. It would confirm we're not alone in the universe, answering one of humanity's oldest questions. It would suggest that interstellar travel, while difficult, is possible. It would reveal that other intelligences view our solar system, and perhaps Earth specifically, as worthy of investigation. It would fundamentally alter our understanding of our place in the cosmos. But again, and this cannot be emphasized enough, this remains pure speculation. No evidence currently supports the probe hypothesis over natural explanations. The scenario serves to illustrate what we might look for, how we might think about detection, and what implications would follow if the highly unlikely turned out to be true. For now, science proceeds with the assumption that this object is natural, while remaining open to evidence that might suggest otherwise. This object, whether natural or artificial, exists within a broader context that has puzzled scientists for decades, the Fermi paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" During a 1950 lunch discussion, the paradox highlights the apparent contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for them. The mathematics supporting the existence of alien intelligence are compelling. The Milky Way contains between 200 and 400 billion stars. Many of those stars host planetary systems. NASA's Kepler mission has confirmed thousands of exoplanets, and statistical analysis suggests nearly every star has at least one planet. A significant fraction of those planets reside in the habitable zone, where liquid water can exist on the surface. If even a tiny percentage of habitable planets develop life, and if even a tiny fraction of those develop intelligence, and if even a tiny fraction of those achieve technological sophistication, the galaxy should be teeming with civilizations. Yet, we see nothing. No radio signals bearing the unmistakable signature of intelligence. No megastructures visible in astronomical surveys. No signs of stellar engineering or galaxy-spanning empires. The cosmos appears silent and empty, devoid of the bustling civilizations that probability suggests should exist. This is the great silence, the eerie absence of cosmic company despite seemingly favorable odds. A Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative civilizations in our galaxy. The equation multiplies factors, including the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life develops, the fraction where intelligence emerges, the fraction that develops technology, and the length of time such civilizations remain detectable. Depending on the values assigned to these uncertain parameters, the Drake equation produces estimates ranging from "we are alone," n equals 1, to "there should be thousands or millions of civilizations in the galaxy." The uncertainty spans orders of magnitude because we have hard data for only some factors. We know the rate of star formation reasonably well. We're beginning to understand the prevalence of planets and habitable zones. But we have no data on the likelihood of life emerging, intelligence evolving, or civilizations persisting long enough to be detected. Numerous solutions to the Fermi paradox have been proposed, each with different implications for objects like our current subject. The rare Earth hypothesis suggests that while simple life might be common, the specific conditions required for complex, intelligent life are extraordinarily rare. Perhaps Earth's large moon, Jupiter's gravitational shielding from asteroids, our position in the galaxy, plate tectonics, or other factors create a unique combination that rarely occurs. Under this model, we might be alone or nearly alone, and this object is certainly natural. The Great Filter hypothesis proposes that somewhere between prebiotic chemistry and galaxy-spanning civilization, there exists a barrier, a step so difficult that almost no species successfully passes through it. The terrifying uncertainty is whether this filter lies behind us. We've already passed the hard step, perhaps the origin of life itself, or ahead of us. We haven't yet encountered the insurmountable challenge that dooms civilizations. If the filter lies ahead, perhaps nuclear war, artificial intelligence gone wrong, environmental collapse, or something we can't yet imagine, then the silence makes sense. Civilizations don't last long enough to colonize the galaxy or send countless probes into the cosmos. The zoo hypothesis, or non-interference principle, suggests that alien civilizations exist and know about us but deliberately avoid contact, treating Earth as a protected wildlife preserve or a sociological experiment. Under this model, probes might observe us from a distance while carefully avoiding detection. Advanced civilizations might have protocols against interfering with emerging intelligences, waiting until we achieve some threshold, perhaps faster than light travel or unification as a species, before making contact. The Berserker hypothesis presents a darker possibility that aggressive civilizations or their autonomous weapon systems destroy emerging intelligences before they can spread. Perhaps the galaxy is dangerous, filled with ancient automated weapons that eliminate potential threats. Any civilization that broadcasts its presence too loudly becomes a target. Under this scenario, the silence is itself a warning, a lesson that survival depends on remaining quiet and hidden. Our own broadcasts into space, barely a century old, might already have marked us for attention from hostile forces. The temporal hypothesis suggests civilizations arise at different times, and the galaxy's habitable period spans billions of years. Perhaps we're among the first technological species' early arrivals in cosmic time. Or perhaps we're among the last, and the galaxy was once filled with civilizations that have long since collapsed or transcended into forms we can't recognize. The window during which two civilizations exist simultaneously and can communicate might be vanishingly narrow. Dr. Robin Hanson, an economist who formalized the Great Filter concept, writes, "The silence could mean we are alone, or that we are among the first, or that some barrier prevents civilizations from lasting long enough or spreading far enough to be visible. Each possibility has profound implications for our future. If the barrier is behind us, we might have an open future among the stars. If it's ahead, our days may be numbered." How does our mysterious object fit into these frameworks? If it were a probe, and we must constantly remind ourselves this remains speculation, it could support the zoo hypothesis. An observational probe would be consistent with advanced civilizations studying us without interference. The object's apparent stealth, if intentional, would suggest a desire to observe without being detected, at least not easily. If the object is natural, it tells us nothing directly about alien intelligence, but reminds us that the cosmos is vast, ancient, and filled with phenomena we haven't yet cataloged. Each unusual object we discover expands our understanding of what's possible in nature. Perhaps the galaxy is filled with natural wonders so diverse and strange that we repeatedly mistake them for artificial constructs. Perhaps the universe's creativity exceeds our own, and the great silence reflects not absence, but our inability to recognize presence in forms we don't expect. This raises profound questions about detection and recognition. How would we know if we encountered an artificial object? What signatures would definitively identify something as manufactured rather than natural? Our current methods rely on narrow assumptions. We look for radio signals at specific frequencies, search for geometric patterns that seem too regular to be natural, or seek chemical signatures that suggest industrial processes. But an advanced civilization might employ technologies we can't imagine, using physics we haven't discovered, communicating in ways we haven't conceived. The quest to detect extraterrestrial intelligence has evolved significantly since the early days of CT, the search for extraterrestrial intelligence. Initially focused on radio signals, the search has expanded to include optical signals, infrared anomalies, and increasingly sophisticated analysis of astronomical data for any signs of technological activity. Yet despite decades of searching, we found nothing conclusive, which forces us to examine our assumptions about what we're looking for and how we're looking for it. Traditional SETI efforts assumed that alien civilizations would broadcast powerful radio signals into space, either deliberately to announce their presence or inadvertently as a consequence of their technological activities. The approach made sense in the mid-20th century when humanity was beginning its own radio broadcasting age. We projected our experience onto the cosmos. If we use radio, surely others do too. Major efforts like the Arecibo telescope in Puerto Rico, now collapsed, and the Allen Telescope Array in California have scanned millions of star systems for narrowband radio signals, the kind that natural processes don't produce. But this approach embeds numerous assumptions. It assumes alien civilizations develop radio technology. It assumes they use it long enough for us to detect it. Perhaps civilizations quickly move to more efficient communication, methods like optical lasers, or even technologies we haven't conceived. It assumes they broadcast in directions we're looking and at times we're listening. It assumes the signals can traverse interstellar space without degradation, or that we can recognize them after such journeys. Each assumption introduces uncertainty. The technosignature approach broadens the search beyond deliberate signals to any signs of technology visible at astronomical distances. This includes megastructures like Dyson spheres or Dyson swarms, hypothetical constructs that capture a significant fraction of a star's energy output. Such structures would create distinctive infrared signatures as they absorb visible light and re-emit it as waste heat. Searches like the glimpsing heat from alien technologies, GHAT, survey have examined millions of galaxies looking for these signatures, finding nothing conclusive. Other technosignatures might include atmospheric pollution on exoplanets industrial, chemicals that wouldn't exist naturally, and that we could detect through spectroscopic analysis of starlight filtered through alien atmospheres. Chlorofluorocarbons, nitrogen dioxide from combustion, or other synthetic compounds might reveal the presence of technological civilizations. NASA's James Webb Space Telescope, now operational, can perform detailed atmospheric analysis of nearby exoplanets, potentially detecting such signatures if they exist at detectable levels. But herein lies a philosophical puzzle that relates directly to our mysterious object. What if we've already detected technosignatures, but don't recognize them as such? What if alien technology doesn't look like we expect? We search for radio signals, but perhaps advanced civilizations use quantum entanglement for instantaneous communication, leaving no electromagnetic signature. We look for Dyson spheres, but perhaps mature civilizations find more efficient energy sources than stellar capture. We seek chemical pollution, but perhaps advanced societies achieve clean technology centuries before becoming visible to distant observers. Dr. Jill Tarter, former director of the Center for SETI Research, captured this uncertainty. We're searching for a needle in a cosmic haystack, and we're not entirely sure what the needle looks like. We might be staring right at evidence of alien intelligence and not recognize it because it doesn't match our preconceptions about what technology should look like. This cognitive limitation, our inability to recognize the genuinely alien, is called the anthropocentric bias. We imagine aliens as biological beings like us, perhaps with different forms, but similar needs and behaviors. We expect them to build cities, use energy, communicate, explore, and create waste products. But what if intelligence can take forms we haven't considered? What if it exists as patterns in electromagnetic fields, as quantum states in stellar cores, as slow-thinking biological computers the size of continents on high-gravity worlds? What if consciousness itself is substrate-independent, and alien minds inhabit forms so different from our neuron-based brains that we can't conceive of them? The philosophical concept of strong anthropic principle suggests the universe's properties allow for observers like us conscious beings capable of asking questions about existence. But nothing requires that we be the only form such observers can take. The cosmos might be filled with intelligences utterly unlike us, operating on timescales we find glacial or frantic, perceiving reality through senses we lack, thinking thoughts structured by entirely different cognitive architectures. Now, circle back to our object. If it is artificial, and we maintain our skeptical stance that this remains unlikely, would we necessarily recognize it as such? Current technology allows us to measure its trajectory, analyze reflected light, estimate its size and composition. But these are crude observations from vast distances. We can't see surface details. We can't detect faint electromagnetic emissions if they're weak or directional. We can't analyze material composition directly. We're essentially examining it from tens of millions of kilometers away with tools designed to study natural objects. If the object were a probe designed to avoid obvious detection, it could easily succeed against our current capabilities. No radio emissions? Then we don't detect them. Surface materials similar to natural asteroids? Then spectroscopy reveals nothing unusual. Subtle anomalies that might indicate internal structure or technology. We might attribute them to measurement uncertainty or natural variation. The probe could hide in plain sight, camouflaged by our own assumptions about what space objects should be. This isn't to suggest that the object is artificial again. Natural explanations remain far more likely. Rather, it's to illustrate the limitation of our search methods. We're getting better at finding what we expect to find: planets, stars, galaxies, black holes, neutron stars. We're less skilled at recognizing the unexpected, especially when it resembles the expected closely enough to avoid triggering our attention. A thought experiment proposed by physicist John Smart, called the transcension hypothesis, suggests that advanced civilizations don't expand outward into space, but inward into increasingly miniaturized and efficient computational substrates. Rather than building Dyson spheres and colonizing galaxies, mature civilizations might optimize themselves into microscale structures operating at maximum thermodynamic efficiency. Such civilizations would become progressively smaller, denser, and less visible from the outside, eventually disappearing from our view entirely, not because they've died, but because they've transcended into forms we can't detect. Under such a model, the galaxy might be filled with advanced civilizations that we'll never find because they're operating at scales or in states we can't observe. The silence isn't because they don't exist, but because they've evolved beyond the phase where they're visible to young civilizations like ours. We're searching for cosmic adolescents like ourselves, civilizations still expanding, still broadcasting, still building large structures. But we might be surrounded by post-biological, post-expansion superintelligences that have moved beyond such crude activities. These speculations venture far from our immediate subject, but provide essential context. The object racing toward the sun exists within a universe where we've detected no obvious signs of alien intelligence despite decades of searching. Either we're alone or nearly alone, or the galaxy operates under rules we haven't yet grasped, where intelligence exists but remains hidden, where technology takes forms we don't recognize, where civilizations follow trajectories we haven't imagined. Let's venture into the hypothetical realm and explore a question that science fiction has examined, but science rarely addresses. If this object were confirmed to be artificial probe, sent by another intelligence, how would humanity respond? What protocols exist? What institutions would coordinate our reaction? What would happen in the hours, days, and months following such a confirmation? The reality is sobering. We have no comprehensive, internationally agreed upon protocol for responding to confirmed contact with extraterrestrial intelligence. While various organizations have proposed frameworks, none have been formally adopted by world governments. We're institutionally unprepared for what would be the most significant discovery in human history. The International Academy of Astronautics developed the Declaration of Principles Concerning Activities following the detection of extraterrestrial intelligence in 1989, updated in 2010. This document outlines recommendations: verify the discovery through independent confirmation, inform relevant authorities, announce the discovery publicly, protect the relevant frequencies from interference, and coordinate international response through the United Nations. These are suggestions, not binding protocols, and many nations haven't formally endorsed them. The United Nations maintains the Committee on the Peaceful Uses of Outer Space, COPUSE, which could theoretically coordinate international response. The Office for Outer Space Affairs, part of the UN Secretariat, might serve as a clearinghouse for information. But these institutions were designed primarily to coordinate peaceful space exploration and prevent military conflict in orbit. They're not equipped to manage the sociological, political, and philosophical implications of confirmed extraterrestrial intelligence. If credible evidence emerged that our object was artificial, the discovery process would likely unfold as follows. First, the observing team would verify their data internally, checking for instrumental errors, software bugs, or misinterpretation. This verification could take days or weeks. Extraordinary claims require extraordinary evidence, and no astronomer wants to announce a false positive that damages their credibility. Second, the team would seek independent verification by sharing their findings with trusted colleagues at other institutions, requesting they observe the object with different instruments using different methods. If multiple independent teams confirm the anomaly using diverse approaches, confidence grows that the observation is genuine rather than systematic error. Third, the discovery would be reported to relevant authorities, likely national space agencies, NASA, ESA, JAXA, Roscosmos, and possibly national security organizations, depending on the nation where discovery occurred. This is where institutional response begins and where information control becomes an issue. Would governments immediately share the finding publicly, or would there be a period of classified analysis? Fourth, assuming the information isn't suppressed, and there are arguments both for and against immediate public release, the discovery would be announced through scientific channels, papers submitted to journals, presentations at conferences, press releases through institutional public affairs offices. The news would spread through scientific communities before reaching mainstream media. Dr. Seth Shostak, senior astronomer at the SETI Institute, has discussed this process. If we detect a signal, or in this case, an object that appears artificial, we'd follow verification protocols before announcing anything. But in the modern world, information leaks. Someone tweets, someone posts to a forum, journalists get wind of it. The idea of a carefully controlled disclosure where institutions manage the narrative start to finish is probably unrealistic. It would be messy, filled with speculation and premature claims. Media response would be intense and immediate. The discovery would dominate news cycles globally. Every expert and many non-experts would be called to comment. Social media would explode with theories, fears, hopes, and misinformation. Religious leaders would be asked about theological implications. Politicians would be pressed for statements. Financial markets might experience volatility as investors try to assess implications for various sectors. Public reaction would likely span a spectrum. Some would greet the news with excitement and wonder confirmation that we're not alone, that the cosmos contains other minds, that perhaps communication or even contact might be possible. Others would respond with fear concerns about intentions, capabilities, and threat. Historical analogies to colonization, where technologically advanced societies encountered less advanced ones with catastrophic results for the latter, would be invoked repeatedly. Religious communities would face profound questions. Some theological frameworks accommodate extraterrestrial intelligence readily, the cosmos as gods. Creation might include many forms of life and consciousness. Others might struggle with implications for doctrines centered on humanity's unique spiritual status. Islamic, Hindu, and Buddhist traditions, with their more expansive cosmologies, might find accommodation easier than traditions emphasizing humanity's uniqueness. Scientific institutions would mobilize resources to study the object more intensively. Every available telescope would be redirected toward it. Funding for rapid mission development would be sought. Could we launch a probe to intercept the object, photograph it up close, analyze its composition directly? The technical challenges would be immense. Our fastest spacecraft travel at roughly 17 kilometers per second. The object is traveling at 87 kilometers per second. Matching its velocity would require propulsion capabilities beyond current technology, though not beyond physics. International cooperation would be essential and potentially challenging. Scientific data sharing might be straightforward. The astronomical community already operates with strong norms of openness and collaboration. But political tensions could intrude. Would nations cooperate fully, or would some withhold information they consider strategically important? Would the United Nations effectively coordinate response, or would major powers pursue independent policies? The question of attempting communication would arise immediately. Should we try to signal the probe? If it's been observing us, it likely already knows we're here and technologically capable. Active attempts at communication might involve radio transmissions directed at the object, powerful laser signals, or other methods. But this raises the METI debate, messaging to extraterrestrial intelligence, which some scientists consider reckless. Broadcasting our presence loudly might attract unwanted attention if the galaxy contains hostile actors. Others argue that the decision has already been made. We've been broadcasting radio and television into space for a century. Dr. Stephen Hawking, before his death, expressed caution about contact. If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. We only have to look at ourselves to see how intelligent life might develop into something we wouldn't want to meet. Others are more optimistic. Dr. Carl Sagan advocated for openness and the search for contact, believing that any civilization advanced enough for interstellar travel would likely be past its violent adolescent species that destroy themselves, don't persist long enough to develop such technology. The debate continues among scientists, ethicists, and policymakers. Practically, our response options would be limited. We could observe intensively, gathering every possible piece of data before the object leaves our observation range. We could attempt to send a mission to intercept it, though the technical challenges make this unlikely in the short term. We could broadcast signals toward it, hoping for response. Beyond that, we would be largely passive observers of an event unfolding on its own timeline. The psychological impact on human civilization would be profound and unpredictable. Some sociologists and psychologists have studied potential reactions through surveys and thought experiments. Results suggest reactions would depend heavily on the specifics. Does the probe seem benign or threatening? Does it respond to our attempts at communication? Is it still functional, or is it a derelict from a long-dead civilization? Each scenario produces different emotional and intellectual responses. One near certainty: the discovery would unite humanity in a way few other events could. Faced with confirmation that we're not alone, that other minds exist among the stars, many of our terrestrial conflicts would seem suddenly petty. National boundaries, political ideologies, religious differences all might feel less significant in the face of cosmic perspective. Or perhaps that's naive optimism. History shows humans are remarkably capable of maintaining local conflicts even during global crises. What we wouldn't do, contrary to science fiction scenarios, is immediately assume threat or launch military operations. A probe millions of kilometers away, traveling through our solar system on a trajectory that doesn't intersect Earth, poses no immediate danger even if its origins are artificial and alien. Panic would serve no purpose. Measured, scientific analysis would be the appropriate response, combined with public communication to prevent misinformation and societal disruption. One crucial question that would arise in the aftermath of such a discovery is whether information should be shared openly or controlled carefully. This isn't about conspiracy theories or government cover-ups in the dramatic sense. It's a legitimate question about information management during periods of potential social disruption. Arguments for transparency are strong and rooted in democratic principles and scientific norms. The public has a right to know about discoveries of this magnitude. Science operates best through open sharing of data, allowing global expertise to contribute to analysis and interpretation. Suppressing or delaying information risks credibility, if the truth eventually emerges. As it almost certainly would, institutional trust would be damaged. The astronomical community operates globally with strong norms against secrecy. Data from major observatories are typically released publicly after brief proprietary periods, and scientists routinely share findings with international colleagues. Furthermore, in the modern information environment, maintaining secrecy would be extraordinarily difficult. Dozens or hundreds of scientists and technicians would have access to the data. Astronomical observations can be independently replicated by numerous facilities worldwide. Amateur astronomers with sophisticated home equipment contribute meaningfully to observations. The likelihood of maintaining information control for any significant period is vanishingly small. Attempts to do so would probably fail, creating exactly the panic and distrust they aim to prevent. Dr. John Rummel, former NASA Planetary Protection Officer, notes, "Science works best in the light. The moment you start classifying discoveries or withholding data, you lose the collaborative advantage that makes science effective. You also sow distrust, and in a scenario involving potential extraterrestrial intelligence, trust is essential for managing public response." Arguments for controlled disclosure, however, also carry weight. Information released during crises requires careful communication to prevent misunderstanding, panic, or harmful behaviors. Announcing "we've detected an artificial object" without sufficient context, evidence, and expert interpretation could trigger irrational fears, market instability, or social disruption. Taking time to prepare comprehensive information packages, educate communicators, and coordinate with institutions isn't censorship, it's responsible information management. There's also the national security dimension, though it's often overstated. If the object displayed capabilities that suggested advanced propulsion, materials science, or other technologies applicable to military purposes, some governments might classify certain analyses. The line between scientific openness and strategic security isn't always clear. Most scientists would argue that information about an object millions of kilometers away, traveling through empty space, poses no security risk and should remain fully public. The citizen science movement adds complexity to information control considerations. Amateur astronomers globally contribute meaningful observations to professional research. Networks like the International Astronomical Union's Minor Planet Center accept reports from qualified amateurs. These contributors would be observing the same object, generating independent data, sharing findings through their own communities. Any attempt to control information would need to account for this distributed, decentralized observation network, which is to say, effective information control would be essentially impossible. Historical analogies provide mixed guidance. When Oumuamua was discovered, information was shared openly and rapidly. Papers appeared on preprint servers within days. Media coverage was extensive. Public interest was high, but did not trigger panic or disruption. The precedent suggests open sharing works well for astronomical discoveries, even unusual ones. On the other hand, Oumuamua wasn't confirmed as artificial. It remained ambiguous, allowing skeptics and believers to coexist comfortably. Confirmed artificial origin might trigger stronger reactions, requiring more careful communication. The balance between skepticism and openness might manifest as staged disclosure, initial announcement of an unusual object, followed by open sharing of data while scientists analyze it, leading to progressively refined interpretations as evidence accumulates. This allows the scientific process to operate transparently while giving the public time to absorb information, gradually rather than being hit with a single dramatic revelation. Dr. Catherine Denning, an anthropologist who studies SETI's social implications, advocates for public engagement. We shouldn't underestimate people's capacity to handle profound discoveries. Yes, some will react with fear or construct conspiracy theories, but most people are capable of thoughtful responses to extraordinary information when it's presented clearly and honestly. Treating the public as fragile or irrational becomes a self-fulfilling prophecy. There's also the question of what happens after initial discovery. If the object is indeed artificial and continues out of the solar system, do we attempt to follow it? Do we invest resources in developing technologies that might catch up to it, even though such efforts would take decades? Do we dedicate observatories to tracking it as long as possible? These decisions involve resource allocation at national and international levels, requiring public support and policy decisions that can't be made in secrecy. The transparency question extends to interpretation. Scientists might disagree about what the data means. Some might favor exotic explanations. Others might insist on conservative interpretations. Making these debates public allows for broader scrutiny, but also creates confusion as the public witnesses experts disagreeing. Managing these dynamics, where scientific uncertainty is normal and healthy, but appears to non-scientists as lack of consensus, requires sophisticated science communication. Ultimately, in the scenario we're exploring, transparency would almost certainly prevail, not necessarily because institutions choose it, but because enforcing information control would be technically impossible and ethically indefensible. The question becomes not whether to share information, but how to share it effectively, how to communicate complex, uncertain, and profound findings to a global public with varying levels of scientific literacy, diverse cultural contexts, and different emotional reactions to existential questions about our place in the universe. Let's step back from speculation about artificial origins and ground ourselves in the humbling reality of cosmic scale. Whether this object is natural or artificial, whether it represents anything more than an unusual space rock, its journey from wherever it originated to our solar system embodies distances and timescales that strain human comprehension. If the object originated in interstellar space from another star system, its journey measured in light years. A light year, the distance light travels in a vacuum over 1 Earth year, equals approximately 9.46 trillion kilometers, or about 5.88 trillion miles. To put this in perspective, light from the sun reaches Earth in about 8 minutes. It takes light over 4 years to reach us from Proxima Centauri, the nearest star system. The object we're discussing, traveling at 87 kilometers per second, moves at roughly 0.029% of light speed. At that velocity, crossing a single light year requires about 34,000 years. If this object originated from even the nearest star systems, Proxima Centauri, Alpha Centauri A and B, or Barnard's star, its journey consumed at minimum 136,000 years, assuming it came from Proxima and traveled in a straight line at constant velocity. More likely, if it came from interstellar space, the journey took hundreds of thousands of millions of years. The object has been traveling through the void since before modern humans emerged, since before Neanderthals walked Europe, since the last ice age was merely a future chill in Earth's climate cycles. Consider what that journey entailed. Traveling through the vast emptiness between stars, the object encountered near-perfect vacuum, perhaps a handful of hydrogen atoms per cubic centimeter, an emptiness more complete than anything achievable in Earth laboratories. Temperatures approached absolute zero, just a few degrees above the cosmic microwave background radiation that permeates the universe. No sunlight warmed its surface. No planetary gravitational fields deflected its path. It moved through darkness so complete that distant galaxies would provide the only illumination pinpricks of light, representing billions of stars condensed into faint smudges. The isolation is almost incomprehensible. For hundreds of thousands of years, this object was utterly alone. The nearest substantial mass might have been light years away. No witness observed its passage. No instrument detected it. It existed in a state of cosmic solitude that we can describe mathematically, but barely grasp emotionally. If the object is artificial, if it contains instruments still functioning, those instruments have recorded the longest, loneliest journey in any database of exploration. Now, it approaches the inner solar system, where matter density increases dramatically compared to interstellar space. It enters the sun's gravitational well, its trajectory bending as it falls inward. It passes through the orbits of outer planets, Neptune, Uranus, Saturn, Jupiter, each a world of storms and moons, each representing a gravitational influence that subtly affects trajectory. It crosses the asteroid belt, where millions of rocks orbit in the space between Mars and Jupiter. It enters the realm of the inner planets, where rocky worlds bask in solar warmth. The object's view, if it could be said to have a view, would change dramatically. The sun, a mere point of light when the object was far beyond Neptune, swells into a disk, then into a blinding sphere dominating the sky. Planets appear as wandering points of light, their positions shifting against the background stars. If the object passes close enough, Earth might be visible, a blue-white sphere, distinctive among solar system bodies for its color and its thin envelope of atmosphere. For us, watching from Earth, the object's appearance in our skies represents a moment, weeks, or months of observation before it passes beyond our ability to study it in detail. For the object, this passage represents the destination or waypoint of a journey incomprehensibly longer than the moment. The asymmetry in timescales reminds us of our cosmic youth. Humanity has existed as a species for perhaps 300,000 years. We've had civilization for roughly 10,000 years. We've had radio for 130 years. We've had spaceflight for 68 years. On cosmic timescales, we've barely opened our eyes. Our radio signals, the unintentional broadcasts that announce our presence to any who might listen, have spread outward at light speed for just over a century. They form a bubble approximately 130 light years in radius, containing perhaps a few thousand star systems. That bubble represents a tiny fraction of our galaxy, which spans 100,000 light years. Most of the Milky Way has no idea we exist. We've been shouting into the void for barely an instant in cosmic time. If alien civilizations exist, and if they sent probes to explore the galaxy, those missions might have launched millions of years ago. The probes might still be operating, maintained by artificial intelligence, or programmed with purposes we can't imagine. They might be derelict, their creators long extinct. They might be part of a network of millions or billions of probes spread across the galaxy in a vast observational survey. Or they might not exist at all, and the entire speculation is human projection onto natural phenomena. Statistical considerations from the Drake equation suggest that if technological civilizations are common and long-lived, the galaxy should contain millions of them. If even a tiny fraction engage in interstellar exploration using self-replicating probes, the galaxy could be thoroughly explored on timescales of millions of years long by human standards, but brief compared to the Milky Way's age of 13.6 billion years. The absence of obvious evidence for such exploration, sometimes called the Fermi-Hart paradox, suggests either civilizations are rarer than optimistic estimates predict, or they don't engage in large-scale exploration. Or they do, but we haven't recognized the evidence. The object before us, natural or artificial, reminds us that space is vast and mostly empty. Distances between interesting objects, stars, planets, comets, are enormous compared to the objects themselves. The solar system is not a crowded place. It's a sparse collection of tiny specks separated by distances that require years to cross even at the fastest velocities we can achieve. The nearest star system, despite being nearby in galactic terms, remains so distant that no human-made object will reach it for tens of thousands of years. Yet here we are, on a small world orbiting an average star in an unexceptional region of a typical spiral galaxy, looking outward with increasingly sophisticated instruments, detecting objects millions of kilometers away, calculating their trajectories, analyzing their compositions, and asking profound questions about what they might represent. In the grand scope of cosmic history, our ability to do this is recent, a development of the last few decades, as technology reached thresholds necessary for systematic sky surveys and detailed observations. Let's shift our tone toward optimism and appreciation for what this object, unusual though it may be, represents for science and human knowledge. Whether natural or artificial, whether mundane or revolutionary in its implications, the detection and study of this object embody the best of human curiosity and institutional collaboration. The discovery itself is a triumph of technology and coordination. The Pan-STARRS survey telescopes, which made the initial detection, represent decades of development in astronomy. The systems automatically scan the sky, identifying moving objects, processing thousands of images, and flagging anomalies for human review. This automated approach allows astronomers to monitor vast regions of sky continuously, detecting objects too faint or fast-moving for human observers to spot visually. The technology didn't exist 50 years ago. Now it operates routinely, expanding our knowledge of the solar system's population. Follow-up observations required global cooperation. Observatories in Hawaii, Chile, Spain, and Australia contributed data, coordinating observation windows, and sharing results in real time. This collaboration happens routinely in modern astronomy, facilitated by international agreements, professional networks, and shared commitments to advancing knowledge. Political tensions between nations rarely interfere with scientific cooperation at this level. Astronomers in different countries, often from nations with strained diplomatic relations, work together seamlessly because the questions they're pursuing transcend terrestrial politics. The data collected represent the cutting edge of observational astronomy. Spectroscopic analysis requires instruments that can split faint light from distant objects into component wavelengths, measuring intensity at each wavelength with high precision. The techniques involved combine optics, electronics, computer science, and physics in systems of remarkable sophistication. Every observation adds to humanity's collective understanding, whether the results show something expected or something anomalous. The transparency of the scientific process deserves recognition. Most observations from major facilities become publicly available after brief proprietary periods. Papers are published in peer-reviewed journals, where methods and conclusions can be scrutinized by experts worldwide. Data is archived in repositories where future researchers can access it, potentially discovering patterns the original observers missed. This openness accelerates progress and ensures quality through distributed peer review. Citizen scientists have contributed meaningfully to the study of near-Earth objects and comets. Amateur astronomers with backyard telescopes and CCD cameras regularly discover comets, track asteroids, and contribute data that supplement professional observations. Organizations like the American Association of Variable Star Observers and the British Astronomical Association coordinate amateur contributions, integrating them into professional research. This democratization of astronomy means that people worldwide can participate in discovery and contribute to knowledge. The object's unusual characteristics, rather than being cause for alarm, represent opportunity for scientific advancement. Every anomaly is a potential window into new understanding. When observations don't match predictions, the discrepancy either reveals errors in our methods, leading to improved techniques, or indicates genuine phenomena we haven't yet explained, leading to new physics or astronomy. Either outcome advances knowledge. Historical precedents remind us that astronomical anomalies often resolve into understood phenomena after sufficient study. The planet Uranus displayed orbital irregularities that couldn't be explained by known gravitational influences. Rather than invoking exotic physics, astronomers hypothesized an undiscovered planet whose gravity was affecting Uranus's orbit. That prediction led to Neptune's discovery in 1846, a triumph of mathematical astronomy. Similarly, Mercury's orbital precession couldn't be explained by Newtonian gravity alone, but rather than abandoning physics, the anomaly eventually helped confirm Einstein's general relativity. Our current objects' anomalies might resolve similarly. Perhaps they indicate compositional mixtures we haven't seen before, but that natural processes can produce. Perhaps they reflect formation in unusual regions of the protoplanetary disk or the Oort cloud. Perhaps they result from processing by cosmic rays over billions of years in unique ways. Each possibility opens research directions that will deepen understanding of solar system formation, compositional diversity, or radiation processing of materials in space. Even if the object proves completely ordinary after more detailed study, perhaps the anomalies result from measurement. Uncertainties that shrink with better data, the exercise of studying it will have value. The techniques developed or refined during the observation campaign can be applied to future discoveries. The institutional coordination demonstrated will inform responses to future unusual objects. The public engagement might inspire young people to pursue careers in astronomy or space science, creating the next generation of researchers. The funding invested in observations telescope time, computational resources, researcher salaries represent society's commitment to understanding the universe. This commitment should be celebrated. In a world facing numerous challenges, humanity still allocates resources to pure knowledge, to questions about cosmic origins and the nature of celestial objects. This represents an optimistic investment in long-term understanding over short-term utility. Dr. Sarah Seeger, reflecting on astronomical discovery, offers perspective. Every object we study, every spectrum we analyze, every orbit we calculate adds another piece to the grand puzzle of how the universe works. Sometimes pieces fit where we expect. Sometimes they don't. And those moments of surprise are when we learn the most. This object, unusual as it appears, is teaching us something either about the diversity of natural objects or about the limits of our detection methods. Either lesson is valuable. The theoretical work stimulated by unusual observations also has value. Scientists are now considering what range of natural processes might produce the observed characteristics. Papers will be published exploring formation scenarios, composition models, or dynamical histories that could explain the data. Even if these specific models don't perfectly match this specific object, they expand the catalog of possibilities, preparing us for future discoveries. The public interest generated by astronomical mysteries shouldn't be dismissed as mere spectacle. When people engage with questions about unusual objects, about the possibility of life beyond Earth, about the nature of the cosmos, they're participating in the ancient human tradition of looking upward and wondering. This sense of wonder is foundational to scientific inquiry. It motivates the young to study science. It justifies to taxpayers and policymakers the investment in space exploration and astronomy. It reminds us that existence includes questions larger than our immediate concerns. Social media, despite its flaws, allows real-time engagement with astronomical events. When something interesting occurs in the sky, millions can participate in discussions, share images, ask questions, and learn from experts. Astronomers increasingly use Twitter, YouTube, and other platforms to communicate discoveries and explain methods. This direct connection between scientists and public bypasses traditional media gatekeepers, allowing for nuanced, accurate communication. The international cooperation evident in observing this object mirrors broader trends in space exploration. The International Space Station involves astronauts and resources from multiple nations. The James Webb Space Telescope resulted from collaboration between NASA, ESA, and the Canadian Space Agency. The Square-Kilometre Array, under construction in Australia and South Africa, involves dozens of countries. These collaborations demonstrate that humans can work together toward shared goals despite political differences. Let's take a technical deep dive into how we detect and characterize objects like this one, demystifying the process and empowering understanding of what we know and how we know it. The science of asteroid and comet detection has evolved dramatically over recent decades, transforming from occasional visual discoveries to systematic automated surveys. Detection begins with repeated imaging of the same patch of sky. Telescopes photograph a region, then photograph it again hours or days later. By comparing images, astronomers identify objects that have moved against the background of distant stars. Stars, being light years away, appear stationary over short timescales. Solar system objects, asteroids, comets, move noticeably, their positions shifting measurably between images. Modern survey systems like Pan-STARRS use large-format CCD cameras, essentially very sophisticated versions of digital camera sensors, mounted on telescopes with wide fields of view. Each image captures millions of stars and potential solar system objects. Computer algorithms automatically compare successive images, identifying moving objects and flagging them for further analysis. The system processes hundreds of gigabytes of data nightly, identifying thousands of potential objects, most of which are already known asteroids, and a few of which are new discoveries. Once a moving object is detected, follow-up observations determine its trajectory. By measuring the object's position at multiple times, astronomers can calculate its orbit using principles of celestial mechanics that date back to Kepler and Newton. The calculations require only position measurements over time and the gravitational constants of the Sun and planets. With enough observations, ideally spanning multiple nights or weeks, the orbit can be determined with high precision. Trajectory calculations account for gravitational influences from all major solar system bodies. The Sun's gravity dominates, but Jupiter's massive gravitational field can perturb orbits measurably. Even the terrestrial planets contribute small influences. Modern orbit calculations use numerical integration methods, essentially simulating the object's motion forward and backward in time by calculating gravitational accelerations at small time intervals. These simulations can predict positions years or decades into the future, or retrodict where the object was in the past. For our mysterious object, orbital calculations revealed the hyperbolic trajectory, an open-ended path that doesn't close into an ellipse around the Sun. This indicates either escape velocity, the object is leaving the solar system permanently, or very high excess velocity from an interstellar origin. The distinction matters for understanding whether the object is a solar system native, being ejected, or an interstellar visitor passing through. Determining size and composition requires different techniques. Measuring an asteroid's size directly is difficult because even nearby asteroids appear as point sources too small to resolve into visible disks. Instead, astronomers measure brightness and make assumptions about how reflective the surface is. A dark object appears dimmer than a bright object of the same size at the same distance. This introduces uncertainty. We can't know the exact size without knowing the exact reflectivity, and we can't know the exact reflectivity without knowing the exact size. Radar observations can break this deadlock for nearby objects. By bouncing radio waves off an asteroid and measuring the return signal's strength and time delay, astronomers can determine distance with extreme precision and measure size independent of brightness. Radar can even create low-resolution images showing an object's shape. However, radar requires the object to be relatively close, typically within a few million kilometers, and have a trajectory that brings it near Earth. Our current object may be too distant for effective radar imaging, depending on its trajectory. Spectroscopy reveals composition by analyzing reflected sunlight. Different minerals absorb light at specific wavelengths due to the quantum mechanical properties of their chemical bonds. When sunlight reflects off an asteroid, certain wavelengths are absorbed while others are reflected. By measuring which wavelengths are present in the reflected light, astronomers can identify the minerals present on the surface. The process involves splitting light with a prism or diffraction grating, then measuring intensity across the spectrum using sensitive detectors. The resulting spectrum, a graph showing brightness versus wavelength, contains absorption features that fingerprint specific compounds. Water ice absorbs strongly in certain infrared wavelengths. Silicate minerals create characteristic patterns in near-infrared spectra. Organic compounds produce features in ultraviolet and infrared regions. For our object, spectroscopic observations revealed the puzzling mixture of features that don't perfectly match any known asteroid or comet class. This doesn't mean the object is artificial. It means its composition differs from objects we've previously studied in detail. The solar system contains billions of objects, and we've obtained detailed spectra for only thousands. Most remain uncharacterized. Finding objects with unusual spectra should be expected as we survey more of the population. Photometry measuring how brightness changes over time reveals rotation. As an irregularly shaped object spins, its cross-sectional area, as seen from Earth, changes, causing brightness to vary. By measuring these variations and their period, astronomers can determine rotation rate and sometimes infer shape. A uniformly bright object with regular brightness variations likely has an elongated shape and regular rotation. Irregular or chaotic variations suggest either tumbling motion or very irregular shape, or surface patches with different reflectivity. Our object's irregular photometry complicates characterization. Is it tumbling? Is it shaped like a potato with dramatically different dimensions? Does it have a surface with bright and dark regions? All are possible, and distinguishing between scenarios requires more data than currently available. Cometary activity, outgassing visible as a coma or tail, is detected through imaging and spectroscopy. As comets approach the Sun, warming causes ices to sublimate, releasing gas and dust. The gas creates a Coleman and extended fuzzy cloud surrounding the nucleus. Spectroscopy of the coma reveals what molecules are being released: water, carbon monoxide, carbon dioxide, methanol, and many others. The dust reflects sunlight and can be pushed by solar radiation pressure into a tail pointing away from the Sun. This object shows minimal cometary activity despite approaching temperatures where ice should sublimate. This could mean several things. Perhaps it's an asteroid with no significant ice content. Perhaps it's a dead comet whose surface has been sealed by a layer of dust and organics that insulates interior ice. Perhaps it's a dormant comet that will activate closer to the Sun. Or perhaps it has unusual composition that doesn't sublimate at expected temperatures. The scientific method in action throughout this investigation deserves emphasis. Astronomers observe, measure, analyze, form hypotheses, and test them against additional observations. When data contradicts expectations, they revise hypotheses rather than discarding data. When multiple explanations fit the data, they acknowledge uncertainty and gather more observations to distinguish between possibilities. This process is slow, careful, and designed to minimize error and prevent jumping to unwarranted conclusions. Looking forward, this object and others like it drive development of new observation capabilities and space missions that will deepen our understanding of the solar system and our place within it. The era of discovery is accelerating, and the next decade promises revelations that will dwarf our current knowledge. NASA's Near-Earth Object Surveyor mission, scheduled for launch in the late 2020s, will significantly enhance our ability to detect and characterize asteroids and comets. This infrared space telescope will find objects that are dark and hard to detect with ground-based visible light telescopes. Infrared observations measure thermal emission, the heat radiated by objects warmed by the Sun, providing size estimates independent of albedo assumptions. The mission aims to catalog 90% of near-Earth objects larger than 140 meters within a decade of operation. The Vera C. Rubin Observatory, under construction in Chile, will revolutionize sky surveys when it begins operations. This facility will photograph the entire visible sky every few nights, creating a continuously updated map that reveals anything that moves or changes. Its unprecedented survey speed and depth will discover thousands or millions of new asteroids, comets, and other transient phenomena. Among these discoveries will likely be more unusual objects that challenge our understanding and require follow-up study. The European Space Agency's Comet Interceptor mission, selected for launch in 2029, represents a new approach to studying pristine comets. Rather than targeting a specific known comet, the spacecraft will wait in space until a promising target, dynamically new comet entering the inner solar system for the first time, or possibly an interstellar interloper, is discovered. Then it will maneuver to intercept the object, flying past at close range with instruments that can photograph, measure, and analyze its composition directly. This mission could transform our understanding of unusual objects. If something like our current subject appears while Comet Interceptor is operational, and if trajectory and timing align, we might get the first close-up images and measurements of such an anomaly. Seeing surface details, measuring composition directly, and observing the object from multiple angles simultaneously could resolve many current uncertainties. China's space program is developing ambitious asteroid and comet missions. The Zhenghe mission aims to sample a near-Earth asteroid and conduct a flyby of a main belt comet. These missions represent growing international capacity for direct exploration of small solar system bodies, expanding the number of objects we can study in detail beyond remote observation. Private space companies are also entering the field. While their primary focus is on commercial opportunities, asteroid mining, space manufacturing, tourism, their development of cost-effective launch systems and spacecraft makes scientific missions more affordable. The decreasing cost of space access will enable more ambitious missions that would have been prohibitively expensive under previous economic models. The ongoing characterization of Oumuamua through archived telescope data continues as astronomers apply new analysis techniques to existing images. Machine learning algorithms, trained to identify subtle signals in noisy data, might extract information from observations that human analysts missed during initial review. These retrospective studies often yield new insights years after the object has left observation range. Theoretical work exploring the conditions that produce unusual objects will guide future observations. Understanding what natural processes can create specific spectral signatures, shapes, or dynamical properties helps observers know what to look for and how to interpret what they find. This symbiotic relationship between theory and observation drives progress in planetary science. The next interstellar object discovered will receive intense scrutiny informed by lessons from Oumuamua and our current subject. The astronomical community is better prepared now observation protocols have been refined. Analysis pipelines are established, and institutions know how to coordinate rapid response. Future discoveries will benefit from this preparation, yielding higher quality data and faster characterization. SETI efforts continue to evolve, incorporating lessons from astronomy's expanding catalog of unusual objects. The Breakthrough Listen project, funded by private philanthropy, conducts the most comprehensive search for technosignatures to date. Using major radio and optical telescopes, the project surveys millions of star systems for signals that might indicate technological activity. While no confirmed detections have occurred, the search continues with improving sensitivity and coverage. The James Webb Space Telescope's ability to characterize exoplanet atmospheres might lead to indirect evidence relevant to questions about life and intelligence beyond Earth. If biosignature gases oxygen, methane, phosphine are detected in exoplanet atmospheres in combinations difficult to explain through abiotic chemistry, we might infer the presence of life even without direct detection. Such discoveries would transform our understanding of life's prevalence and indirectly inform questions about intelligence and technological civilizations. Future space missions might target unusual objects intentionally. If an object with particularly anomalous characteristics is discovered with sufficient advance notice, space agencies might develop dedicated missions to study it. The scientific return from close study of a genuinely unique object could justify significant investment, especially if the object's characteristics suggest importance beyond normal asteroids or comets. The accumulation of data from all these sources ground surveys, space telescopes, direct missions, theoretical work will eventually provide context that might resolve current mysteries. Perhaps our unusual object will prove to be one example of a previously unrecognized class of solar system body that becomes commonplace once we know to look for it. Or perhaps it will remain unique, a tantalizing anomaly that drives decades of follow-up research. Regardless of outcome, the pursuit itself justifies the effort. We explore not only to find answers, but because the search itself embodies what makes us human: curiosity, persistence, and the drive to understand. Each discovery, whether revolutionary or incremental, adds to the grand edifice of knowledge that future generations will build upon. We are part of a continuity of inquiry, stretching back to the first humans who looked upward and wondered what those points of light might be, and stretching forward to descendants who might navigate between stars and answer questions we haven't yet thought to ask. As this object continues its journey sunward and then back into the cosmic deep, let's take a moment to bid farewell to this mysterious traveler and reflect on what its passage through our solar system has meant for our collective imagination and scientific understanding. Whether you are a rock shaped by blind gravitational collapse in the dark, reaches beyond Neptune, or a shard of ice from the Oort cloud's primordial reservoir, or something stranger that natural processes we've yet to understand brought into being, whether you are the product of 4 billion years of celestial mechanics or the handiwork of minds that looked to the stars long before we evolved, you have captured our attention and our wonder. You arrived from the darkness between worlds, from distances so vast that your journey consumed time measured not in years or decades, but in epochs. You passed through spaces where no human will ever travel in our lifetimes, where the sun is merely one star among countless others, where Earth is invisible, where nothing moves except you, carrying forward momentum imparted long ago by processes we can only reconstruct through mathematics and inference. Now you fall toward the sun, your velocity building as you descend into its gravitational well. You will pass closer to our star than Mercury orbits, bathed in radiation so intense it could vaporize water and melt lead. If you contain ice, as comets do, perhaps you will awaken releasing long frozen volatiles in jets of gas and dust, announcing your presence with a sudden coma and tail. Or perhaps you will remain silent, your surface sealed, your mysteries intact. As you round the sun and begin your outward journey, you will pass through our observational window like a swimmer surfacing briefly before diving back into invisible depths. Telescopes will track you as long as they can, gathering every possible photon of reflected sunlight, extracting every bit of information from your light. But eventually you will fade, becoming too dim to detect, too distant to measure, too far to study. You will return to the cosmic ocean from which you emerged, carrying with you whatever secrets you hold. If you are natural, and you almost certainly are, you represent the solar system's incredible diversity. You remind us that 4 billion years of collisions, migrations, gravitational interactions, and radiation processing have created a population of objects so varied that we've cataloged only the tiniest fraction. Each new discovery expands our understanding of what's possible in nature, what conditions exist in different regions of space, what histories are written in rock and ice and dust. If you are artificial, and you almost certainly are not, you represent something even more profound. You would be evidence that intelligence arose elsewhere, that minds other than our own looked outward and wondered, that technology developed on distant worlds, that purposes we can barely imagine drove the creation of instruments that crossed the interstellar void. You would be a message, not in words, but in existence. We are not alone. Others have asked the same questions. The universe gives rise to consciousness in multiple locations. The story of intelligence is not confined to one small blue planet orbiting an average yellow star. But even uncertainty has value. The very fact that we can ask these questions, that we can imagine these possibilities, that we can gather data and analyze it and debate interpretations, this itself is remarkable. We are a species that evolved from ancestors who struggled for survival in African savannas. And now we point instruments into the night sky, detecting objects millions of kilometers distant, calculating their compositions from reflected light, and pondering whether they might be artificial constructs from alien civilizations. The journey from stone tools to space telescopes consumed 300,000 years of human history, an eye blink in cosmic time. You, mysterious wanderer, have given us a gift regardless of your nature. You've reminded us that the cosmos remains largely unexplored and that surprises await discovery. You've shown us that our classification systems, while useful, remain provisional. Nature produces phenomena that don't fit neatly into categories we've constructed. You've sparked conversations that blend science with philosophy, data with wonder, measurement with imagination. You've also demonstrated the best of human collaboration. Scientists across continents and cultures have worked together to study you, sharing data and insights, contributing their expertise to collective understanding. This cooperation transcends political boundaries and ideological differences. When faced with cosmic mystery, humans remember that we share a planet, a heritage, and a future. We look upward together, united by curiosity. As you continue your journey, carrying forward through space on trajectories that will take you far from this system, know that if consciousness can be attributed to collections of rock and ice, or circuits and sensors, you are not forgotten. Your passage has been recorded. Your spectrum has been measured. Your existence has been documented in archives that will persist as long as human civilization endures. Future astronomers, decades or centuries from now, might review these observations and extract insights we missed. You've become part of our story, a chapter in humanity's expanding understanding of the universe. For those of us who have followed your story, who have watched for updates, read the papers, pondered the implications, and wondered about your nature, you've provided something precious. A reminder that existence is strange and wonderful, that questions remain to be answered, that the universe exceeds our imagination, and that the search for understanding is one of our species' noblest endeavors. Perhaps someday, when humanity has developed technologies we can't yet conceive, we'll send missions to distant regions of the solar system or beyond, seeking to understand objects like you in detail. Perhaps we'll develop propulsion systems that can match your velocity, allowing spacecraft to rendezvous and examine you closely. Perhaps we'll find others like you, and through comparative study, understand what you represent. Or perhaps you'll remain forever mysterious, a puzzle that drives speculation and research, but never fully yields its secrets. And that would be okay too. Not everything needs to be understood completely or immediately. Mystery has value. It motivates exploration. It humbles us with the recognition that our knowledge, extensive as it has become, remains limited. It reminds us that the universe owes us no easy answers, that understanding requires effort and patience, and the acceptance that some questions might not be resolved in our lifetimes. Good night, wanderer. Safe travels through the darkness beyond worlds. May your journey, however long it continues, be stable and undisturbed. May you carry forward through centuries and millennia, through the spaces between stars, through regions of space no human will ever see. And if you hold secrets, whether secrets of composition and formation that science will eventually decipher, or secrets of purpose and origin that would revolutionize our understanding, may those secrets someday be revealed in time and in ways we can comprehend. Thank you for passing through our neighborhood. Thank you for the questions you've raised, the speculation you've inspired, and the reminder you've provided that the cosmos remains full of wonder. We'll continue watching the skies, searching for others like you, building instruments of ever greater power and asking questions about what we find. And when we find the next unusual object, as we surely will, we'll think of you, the wanderer who captured our attention in this particular moment of our civilization's history. Until we meet again, if we ever do, if human missions someday venture far enough to encounter you again in the outer solar system or beyond, we wish you well. Travel safely through the cosmic deep. And know that, for a brief moment, you were important to us, a species of curious primates who evolved on a small world and learned to look upward with wonder and the tools to begin understanding what we see. Now, as we conclude this journey into mystery and speculation, I want to hear from you. What do you think about this unusual object? Does it spark your imagination toward natural explanations, some exotic combination of composition and history we haven't yet considered? Or does it make you wonder whether we're being observed by intelligence beyond Earth? Do you think we should be more aggressive in searching for artificial objects in our solar system? Or should we assume natural explanations unless proven otherwise? Drop your thoughts in the comments below. Share your theories, your skepticism, your hopes, and your concerns. If this deep dive into cosmic mystery resonated with you, if you appreciate the balance between speculation and science, between wonder and skepticism, please consider liking this video and sharing it with friends who enjoy pondering the profound questions about our place in the universe. Subscribe to the channel if you want more explorations of astronomical mysteries, scientific frontiers, and the strange phenomena that remind us how much we have yet to learn. And remember, whether this object turns out to be a completely ordinary comet whose unusual features resolve with better data, or whether it proves to be something genuinely unprecedented that reshapes our understanding, the universe will continue surprising us. The cosmos is vast, ancient, and filled with phenomena we're only beginning to catalog. Every object we study, every spectrum we analyze, every orbit we calculate brings us closer to understanding the grand story of cosmic history and our place within it. Keep looking up. Keep asking questions. Keep demanding evidence while remaining open to possibilities. And keep that sense of wonder alive, the feeling that drove you to click on this video, the curiosity that keeps us exploring even when answers prove elusive. That wonder, that drive to understand, is among humanity's most beautiful characteristics. It's what transforms us from survivors into explorers, from questioners into discoverers, from isolated inhabitants of one small world into a species reaching toward comprehension of the infinite. Thank you for joining me on this journey into the mysterious and the speculative. Until next time, clear skies, fellow seekers of cosmic truth.